Students, we'll start our lesson. This is lecture 4 in Higher Mathematics 2, the chain rule. The chain rule, we call this chain rule Zanjir Qoidasi in Uzbek. So this is the chain rule which we use to calculate the derivative of composite functions. And it's also applicable for functions of two variables. Theorem 5 says chain rule for functions of one independent variable and two intermediate variables. If w equals to f of xy, and it's a differentiable, and if x equals to x of t and y equals to y of t are differentiable functions of t, then the composite w equals to f of x of t, y of t is a differentiable function of t. And we write the following. So this we can write dv dt. So this we can write dv dt, which is the derivative of w with respect to t. T is the independent variable in this case. So in order to calculate the derivative of w with respect to t, first of all, we have to calculate derivative of f, which is our function, w, it's given here, f with respect to x. And inside that, we have to calculate derivative and multiply the derivative x with respect to t. And plus, we have to calculate the derivative of f with respect to y and multiply to the derivative of y with respect to t. Or this form is also common to write dv dt equals to partial derivative of f over dx dt plus df dy times dy dt. To find dv dt, we write down the root from w to t, multiplying derivatives along. You may see in this graph, maybe chart, we call chain rule dependent variable. We have w equals to f of x. It's a dependent variable, and first we have to calculate the derivative of w with respect to x, and then we have to calculate derivative of x with respect to t. Then we'll get this expression. Each of partial derivative of f with respect to x and partial derivative of w with respect to x, or f small x, indicates the partial derivative of f with respect to x. All of them we can write the same way, partial derivative of f with respect to x. For the functions of two variables, two intermediate variables, we may remember the chain rule picture diagram below. To find dv dt, we'll start from w and write down each root to t, multiplying derivatives along the way, then add the products. So I have function w equals to f of xy here, and in order to calculate the derivative of this function with respect to t, first of all I have to calculate its derivative with respect to x, and then multiply this to the derivative of x with respect to t, this one, then plus I have to calculate derivative of w with respect to y, and then multiply the derivative of y with respect to t, this part. If we add this parts together, we'll get the derivative of w with respect to t. We may use the chain rule to find the derivatives of w equals to xy. This is the first example. So it says we have a w which is equals to xy. This is a function, double variable function. It has variable x and y. With respect to t, we need to calculate its derivative with respect to t. Along the path, x equals to cosine of t, y equals to sine of t. What is the derivative's value at t equals to pi over 2? Okay, we may apply chain rule here to find out dv dt as follows. dv dt equals to partial derivative of w with respect to x and dx dt plus partial derivative of w with respect to y times dy dt. Just now we saw we've created this from the previous slide. And here, where does this come from? It says dv dx. So I will write here again in order to be understandable these expressions. dv dt times dx dt. This is from the formula. In the previous page we saw that one. So there is a w. What is w? W is xy in my case. So I will write d dt, not times, like parentheses here, xy instead of w, and times d over dt. Here instead of x, I will write this one, cosine t. Or it also can be written like here, near to the d for on the numerator, times this one is also same, cosine t over dt. So I know how to calculate the derivative of, sorry, it wasn't t, it was x. I did mistake here, and here, and one more here. So it's x. So derivative of xy with respect to x. When we are calculating the derivative of xy with respect to x, the x is a variable, y is a constant. So I will write constant first, y times x. Derivative of x is 1, so I don't have to write it. So derivative of cosine is, I think, negative sine. So open the parentheses, negative sine t with respect to t. So we got this expression from the first part, which is written here also, and the second part also, dv dy dt. So derivative of xy with respect to y, we will get x, and times derivative of y. Y was the sine t. Derivative of sine gives me cosine. So just to simplify this, first of all, just plug in instead of y sine of t, and plug in instead of x cosine of t. I will get this expression here and this one here. So this multiplication gives me negative sine squared plus cosine squared, cosine 2t. You know this because we had this kind of formula, cosine 2 alpha equals to cosine squared alpha minus sine squared alpha. From that one I can write cosine 2t. Now what is left? In the example, in the question says, use the chain rule to find the derivative of w with respect to t along the patch x of x equals to cosine t and y equals to sine t. And here's the question, what is the derivative's value at t equals to pi over 2? So I got the derivative here. Now I have to calculate its value at t equals to pi over 2. Before calculating that, there is another way to check the derivative, which is just plugging in instead of x and y cosine t sine t. So we know this from the formula, sine 2 alpha equals to sine alpha cosine alpha. So I know the formula, so from that we can get this one. Derivative of this expression with respect to t gives us 1 over 2 because it's the coefficient, and derivative of sine 2t gives me the cosine 2t times 2 because we have to take derivative, or we have to use the chain rule again for the function inside of sine, which is 2t. It gives us number 2. So these number 2's are gone, so we got cosine 2t. Now just plug in t equals to pi over 2. 2 times pi over 2, these 2's are gone, cosine pi gives me negative 1. There are some functions of 3 variables. In Theorem 6, chain rule for functions of 1 independent variable and 3 intermediate variables. If w equals to f of x, y, z, and it's differentiable in x, y, z, and it's differentiable in x, y, and z are differentiable functions of t, then w is a differentiable function of t. If you remember, and if you look carefully to this expression, it's the same, except this part. This part is new, but these 2 parts are the previous one, which is the similar for the chain rule for functions of 1 independent variable and 2 intermediate variables. If we have 3 intermediate variables, we just have to add this 3rd intermediate variable's derivative. And we have to calculate this sum together, we'll get the answer. And we may see this in this chart diagram. So I have the function w equals to f of x, y, and z. First of all, I need to calculate the derivative of w with respect to x, with respect to t. calculate derivative of w with respect to y, derivative of y with respect to t, and the last finally w's derivative with respect to z and z's derivative with respect to t. Then calculate the sum, add them together, get the answer. In example 2 it says find dv dt if w equals to xy plus z and x equals to cosine t, y equals to sine t. Z is t. In this case we'll use this rule. Just now we learned, we will use this rule. So what do we need? First of all, we'll need partial derivative of w with respect to x, with respect to y, and with respect to z. So partial derivative of w with respect to x, dv dt, w with respect to x, dv dt times dx dt. Just calculate the first term of this sum. Derivative of w with respect to, it is x, with respect to x gives us y times derivative of x with respect to t, derivative of cosine is negative sine. And derivative of w with respect to y times derivative of y with respect to t equals to, and derivative of w gives me with respect to y, so x times derivative of y with respect to t gives me cosine of t. And the last one, derivative of w with respect to z, derivative of z equals to derivative of w with respect to z gives me 1 times derivative of z with respect to t gives me also 1. So in this case we have here negative y times sine t plus x times cosine t plus 1. So if I plug in instead of y sine t, so negative sine squared t plus instead of x cosine t plus cosine squared t plus 1 equals to cosine t plus 1. Now it says calculate its value at t equals to 0. So this is cosine 0 plus 1. The value of cosine is at point 0 is 1 plus 1 gives us the number 2. 0 is 1 plus 1 gives us the number 2, which is the result of the following example. And we also can write that expression in this beautiful form, which is the derivative of w with respect to t, and calculate its value at point t equals to 0. And the answer is same too, but it's a better way to write that. In this theorem, the chain rule for 2 independent variables and 3 intermediate variables. Okay, suppose that w equals to f of x, y, and z, and x equals to g of r and s, y equals to h of r and s, z equals to k of r and s. If all 4 functions are differentiable, then w has partial derivatives with respect to r and s, given by the formulas. So now we have 2 forms of partial derivatives of w with respect to r and with respect to s. Because the w is a function of 3 variables, it has 2 independent variables. Because of that, we can calculate the w's derivative with respect to r first, and then with respect to s. And in this figures, composite function and branch diagrams for the theorem 7, just now we saw that the w is our function and it has 3 intermediate variables. Each intermediate variable has 2 independent variables, r and s. And how to calculate that? Calculate derivative of w with respect to x, derivative of x with respect to r and others, and then derivative of w with respect to x, derivative of x with respect to s. Add them together, get the answer for the derivative using chain rule. In this branch diagram for the equation, partial derivative of w with respect to r, and it's shown here how to calculate. We have like x and y. or in this case we don't have the third intermediate variable, which is z. If f of xy, w equals to f of xy, which is double variable function, x equals to g of r and s, and y equals to h of r and s, we can use these two formulas together one by one, because we don't have third variable, third intermediate variable z. We don't have in this case. In the branch diagram for differentiating f as a composite function of r and s with one intermediate variable. If there is just one intermediate variable, it's easier to calculate by calculating derivative of w with respect to x and derivative of x with respect to r. The multiplication gives us the partial derivative of w with respect to r, or the vice versa for the derivative of w with respect to s. In this branch diagram for differentiating w with respect to x, setting dv dx equals to 0 leads to a simple computational formula for implicit differentiation. Now, we may use the implicit differentiation rules to calculate the for functions given in implicit form, not the explicit form. We have w equals to f of xy, and dv dx is partial derivative of f with respect to x, and dx, the derivative of x with respect to x, gives us 1, or the partial derivative of f with respect to y, and partial derivative of y with respect to x gives us h prime of x. So the formula will be in this form for now. dv dx equals to f prime x times 1 plus f prime y times dy dx. In the theorem, it's given clear and easy for suppose that the capital letter f of xy is differentiable and that the equation fxy equals to 0 defines the differentiable function of x. Then at any point where f prime y is not 0, this condition holds. The formula is correct. The derivative of y with respect to x equals to negative of partial derivative of f with respect to x divided by partial derivative of f with respect to y. Good luck, guys. We'll see you in the practice part. We have a lot of examples and exercises to solve.